Two more examples here with limits at infinity. Now let's really shake things up. Limit as x approaches infinity, we've got 4x minus 1 all over the square root of 5x squared plus 1. Okay, so now we're going beyond just a rational function. We've got a root thrown in there as well. We're going to use the same technique we did for the previous three problems. We are going to divide each term by the highest power of x in the denominator. But we've got to be careful when we do that. Actually, it'd probably be better to say this right here. Let's divide by the highest effective power in the denominator. And I'm kind of asking, what is the highest effective power in the denominator? Well, I see x squared, but there's also a square root. So the effectiveness is the square root of x squared, which just boils down to x. Okay, so the effective power is x to the first. Okay, so let's see how this plays out. That square root's going to give us some trouble, but we can work with the algebra. I'm going to think of dividing numerator and denominator by x instead of just jumping to doing it by each term, okay? So you see some work here on the right side, but I'm just going to start over here. So I'm dividing the numerator by x. I'm dividing the denominator by x. I didn't feel it necessary to show this step back in the previous problems. I think we all get it. You divide top and bottom by x, but then you can put it to each individual term. Okay, so the numerator is going to work no problem, right? It's going to be 4 minus 1 over x. But this denominator, let's investigate that a little bit further. I've got it out to the side and how the algebra is going to work. What happens when we divide this by x? Think of this x in the denominator as the square root of x squared. Okay, why are we going to do that? Because I have a square root in the numerator as well, I want my denominator to have a square root so that I can then put one big square root around the whole thing. And you may remember that from algebra at some point. If you have the square root of a numerator and denominator, you can put one big square root around everything, like so. Okay, how is this helpful? Well, now I can divide them separately. I can take 5x squared over x squared plus 1 over x squared, and I've got this. Okay, so kind of to say this again. So when we're dividing by x, it's like I'm trying to push that x up inside the square root. Well, in order to push the x up inside the square root, I have to counterbalance the square root. So I have to think of it as x squared when I push it inside. Then I can divide them each separately, like so. And I end up with this guy here. Okay, so I'll take that whole thing, I'll put it back into my denominator, and you can see the rest of my work there. So our numerator, we know, becomes 4 minus 1 over x. Our denominator, the square root of 5 plus 1 over x squared. We've got our limit as x approaches infinity. And now we're going to look at each part separately. So as x approaches infinity for 4, the constant, I just have 4. The 1 over x becomes 0. In the denominator, we have the square root. But remember, if you remember that property from, toward the end of the discussion on continuity, roots are always continuous on their domain. So we can push that limit inside the square root and just take the terms as they are. So, if you think of that limit being pushed inside that square root, then the limit of 5 is 5. And as x approaches infinity, 1 over x squared goes to 0. And so we end up with this nice thing, 4 over the square root of 5. And I'm just going to leave that as my answer. You could rationalize the denominator here if you wanted to, but I kind of like it in this form. We still see it's like that ratio of those first two numbers, right? And there you go. So even back in this one, you know, what would have appeared to have been infinity over infinity turned out to be the ratio of the 4 and the square root of 5. What does that mean for, you know, for a function like this as it's growing? So, you know, numerator and denominator are both going to infinity, but they're doing it in such a way that they're canceling out. So as x values get bigger and bigger and bigger, maybe I should look back at the original. As x values are getting bigger and bigger, sure, these are both getting bigger, but there's this, you know, common, you know, proportion between them that when x gets very, very big, it starts to head towards this y value, a level off. Okay, I think you get it. We got one last example here. Part J, oh my goodness. Okay. We've got some natural logs involved. It's the limit for 2 natural log x over 5 plus natural log x as x approaches infinity. Well, believe it or not, we are going to approach 1 in the same way we've done the last couple of problems. Here, though, you know, we don't have powers of x, but we're still going to divide each of these 3 terms by the same thing. And this would be a lot more interesting if we were all in class together and I could kind of put it out to the class, you know, hey, what do you think we should divide everything by? So that when we take this limit, it'll play out like those last problems. And when I teach the course, usually somebody, at least one person in the room, you know, has an idea and they're typically correct. We're going to divide everything by the natural log of x. Okay, so it's not a power of x, you know, it's like a different operation on x, the natural log, but okay, there's a similarity there. It's something being done to x. Okay, if we divide by natural log x, each of the 3 terms, and you're going to see all my work at this point, what's going to happen? So limit x goes to infinity. We've got 2 on top. 5 divided by natural log x. That will go to 1. What's going to happen as x approaches infinity? Well, the 2 and the 2, the 1 to the 1. 5 over natural log x, that's really the important feature. This is going to head towards 0. Why is that? So I've got a note down below. As x gets bigger, the natural log of x also gets bigger. I don't know if you're familiar with the graph of the natural log of x. I can kind of sketch it. Natural log of x looks like this. It has a vertical asymptote. Here it passes through 1, and then it continues on. And it almost seems like it levels off, but it actually does increase ever so slightly as x moves off to infinity. And so as x goes to infinity, the y value here is going up and up and up, slowly but surely. So that means this denominator is getting bigger and bigger and bigger. So 5 divided by that is getting smaller and smaller and smaller. It's headed towards 0. And that's, you know, the difficult thing to wrap your head around. But once you have that, well, 2 over 1, this is headed towards 2. Okay, that's the end of 2.6. Hey, we're going to talk about the derivative finally in 2.7 next.